No.
No? Okay, now today we move on to continue with the concepts that we started yesterday, and also I'm just going to assign the first projects to you, which hopefully we should be able uh, to uh, to finish the term by completing several projects, which is going to be an interesting ones also. Okay, now the thing which we want to do today, I want to continue from the thing that we finished yesterday. The thing that we finished yesterday, we somehow started with some kind of theoretical stuff that we did, and we were able to find, I should say, the critical point of a quadratic function, which the critical point, I mean, as what we talked about that, I should say yesterday, if I just want to have a very quick, I should say, review of the things that we did, we said that the critical value of a quadratic function, imagine that if that's going to be a quadratic function, f of x, we saw that there is a point always with any quadratic function. There is always one point that you can see that it's just going to be called as, we call that xc. I preferred, as I told you yesterday, I prefer to just remember c as it means crazy, but we call that critical point or the vertex of a quadratic. And we say that so because we noticed that until we reach to this point, and also let me show this one also, which is going to be f of xc. And we noticed yesterday that we call this point a crazy point because when you see that, when you are walking along the x-axis from the left to right, you see that while you are moving towards that direction, until you reach to this point, the function is decreasing, or I just use this cartoon to say that the function is crying, but as soon as you are at this point, the function behavior suddenly changes and the function starts to increase again. And that's why we call that this piece of the function, it's happy. You can think of, we saw that yesterday, we talk these functions like that because with this function, if it's going to be written in a general format as a quadratic functions, we notice that this one, which is going to be the leading coefficients of our function, which is going to be the a, the leading coefficients a is always has to be positive in order to we look up at our graph. And that's what we saw that. If a is negative, you will see that the behavior is going to be different. The function is initially, I should say, laughing, then starts to cry. These points with this very singular behavior, that's what we call that the critical point. Now, all the things that we discussed yesterday was how to find this point. Because essentially at the same time, we saw that as soon as we are able to find this point, we can have a, let's say, a line, which we call that a vertex line. And what does the vertex line would do? We saw that yesterday that this line, if I can write it, the function is going to be x equals to x of c. This line is also serves as a symmetric point, symmetric line with regards to this wing of the plot and with regard to this wing of the plot. Although my plot is not very symmetric because I was not so careful when I plotted this one. But that's what we saw that yesterday, that also we talked about the symmetric behavior of the plot with respect to the vertex line. All the thing that we did yesterday was essentially just centered around this point. We said that how to find this crazy point. We said that this point is gonna be, it's coming from this equation. we said that we are just going to define an equation, which this equation is simply can be written like that. We talked that about yesterday with some, I should say, some interesting, I should say, focus on piece of a function. We saw that this line that we are getting is by this function, this we call that f of x plus h minus f of x divided by h. Somehow we saw that we sometimes we force ourselves to think that in this scenario, h, which we saw that if you remember from yesterday, it was like the distance from the place that you are to go to buy, let's say, a sandwich for dinner, and we say that the distance that we want, we are very lazy. That's why we push h to goes towards 0. And we saw that the equation that we get from this one, imagine if I call that equation, let's say f prime of the x, the prime which I have noted, which I have put here, when you just go to upper years, when you're looking at the calculus, you see that this one has a very interesting name and interpretation. We do not get to that one. We said that when I look at this function, that I say f prime of the x becomes 0, then the roots which I get for this equation, as I call that x naught, that it makes, I should say, f prime of the x equal to 0, then we looked at these points and we said that these points has to be our critical points, which we got that conclusion. X naught has to be our critical points or crazy points of that function. That's essentially a very brief review of what we did yesterday. And now the plan that we have for today is we want to expand the things which we saw yesterday in order to find the local minima and the local maxima, which is a very nice introduction to the optimization theories. It's going to be, the whole session is going to be revolved around that. It's going to be the very last session that we're going to talk about these ones. From tomorrow, we change the gear, we just go to something different. The method which I'm just going to teach you right now is somehow a very general method. The one which you have in the textbook is just for the quadratic function. But if you learn the method which we are just going to cover right now, and also we covered that yesterday, and you did the excellent job on the homework, it's essentially this method is going to be relevant in the advanced functions 12. It's going to be relevant in, I should say, in calculus and vectors class, which you have in the upper year, and also it's going to assist you at the first or the second year of the university if you take a course which involves math. Then please listen to this method, and that's a very general method, which is going to be, it's a global and the universal applications for this. I'm coming here and I say that, okay, I'm going to have a single variable, f of x. There is only one single variable. I'm just going to call that f of x. But why do I call that a single variable? Before I just continue, I just want to say, why do I keep calling a single variable? Because imagine that sometimes you have the chance also to choose two variables and also y. Then you can come here to say that, okay, I'm just going to define a function of two variables. For example, like that, it's x squared plus y squared plus the square root of 2. Look at that. This is still a function, but contrary to what you will see in the functions 11, it has another variable, which it is y. That is why when I say that I pick up a single variable, I always say, I just want to highlight that this one is called multivariate function. The ones which we have is going to be a single variable function. Let me go to the next page then. Then when I say a single variable, I hope that you understand why do I emphasize the fact that it's going to be a single variable. I have a single variable. I'm just going to make a transformation of it, and I call this f of x. And this function is going to be a polynomial function, x cubed minus 3x plus 1. The first thing which you can do is that when you just want to study this function, you may wonder, okay, how that function may look like. The first thing which you do, you can just go to your graphical calculators. You can just go to the Desmos and plot the function and see what's the behavior of that function. I'm not going to go to the plot right now because we are just going to make some prediction of what's going to happen to this function. Then at the very end of the session, we move on to, at the end of the session, we move on to the Desmos to see that if the analytical job that we are doing right now matches of what actually the plot of that function looks like. Then please do not plot the function right now. Just come with me to just do some analytical jobs then. Okay. The first thing that we have to do is that we want to find the vertex or the critical point of this function. In order to do that, you remember from the things that we said yesterday, we come here, we define this function. We said that I'm just going to construct this function. This function, it says that I have to start with f of x plus h minus f of x divided by the h. I'm just going to construct this one, and I know that at the end, I have the h, which is going to be pushed as close as possible, goes to 0. Then the thing which I'm going to do right now is going to be this. I'm going to construct this one. I'm just going to come here to just have a long line. And now look at this. Wherever I see the x, I'm just going to substitute x plus h. That's the strategy. If you remember, we did the same thing yesterday. What's going to happen right now here? The thing which is going to happen right now is here. I'm just going to start with the f of x plus h. I stand on the top of this function and I move forward. Wherever I see x, I remove the x and I plant x plus h. I walk, I reach to this one, it becomes x plus h to the power 3 minus 3 times x plus h plus 1. It is going to be our first term in this equation, which is f of x plus h. That's why I showed that in blue. Okay, now I'm just going to move on to the next step. I know that this one is going to be, I should say, my first term. I put that inside the parentheses. And I know that I have to put the minus sign here. And I move on to find the f of x. For the f of x, I'm just going to write that by green. Wherever you see green, it means that I'm just going to do the same thing. My f of x is going to be very simple. It's going to be x. I have the f of x itself. It's going to be x cubed minus 3x plus 1. And I know that I have to put that in parentheses because minus have an impact on all of it. And I have my h here. I know that the h also has to be pushed close to 0. Okay, now I'm just gonna come here and simplify that formula which I have. But first of all, look at this expression, guys. Look at this one. A 2-term which comes to the power 3. If you remember from the prior years that you studied, I should say, the basic identities, you know that I can write here, here as a note that as an identity, you have a plus b, then all of them goes to the power 3. It becomes this, a to the power 3 plus 3 a to the power 2b plus 3ab to the power 2 plus b to the power 3. That's the identity which you have seen that before. Now, okay, I'm just going to use this one in order to expand the thing which I have right now here to simplify the terms. I'm just going to come here, down here, and I'm just going to simplify the terms. Okay. The first term which I have with the power 3, I'm just going to write this. It's going to be what? I'm just going to write this with this color, which is around there. It becomes x to the power 3 plus 3x squared times h plus 3x h squared plus h to the power 3. You see, I didn't do much except I knew this identity. You can memorize this identity and apply it anywhere when you see two terms that are coming to the power 3. It becomes the first term to the power 3 plus the 3 times of the first term to the power 2 times power to the term 3 plus 3x h squared plus h to the power 3. Now I have minus 3x minus h. That is essentially what I did here. I had 3 multiplied these two terms, then I multiplied these two terms. Then at the end, I have what? I have plus 1. And also, I have this one. I know that I have to impact minus to each term. Then I remove it from the minus sign. Then it's got minus x to the power 3 plus 3x minus 1. Still, I know that I have the h at the denominator, which h has to be pushed towards 0. Okay, now that's the time to do some housekeeping. I just come here to find the similar terms with the opposite sign. Look at this term, x cubed. It's somehow exactly the same thing with x cubed here, but with the opposite sign. It means that you can kill these two terms. And also, look at the other ones. You have, let's say, for example, 3x here, minus 3x, and you have positive 3x. These two terms are also similar. We can get rid of them. And at last, we have one more term, which is minus 1 with the plus 1 over here. You see that? Any questions, guys, so far?
No.
Everyone is doing fine?
Yes, okay.
Great. And now look at that. What's going to happen next? I'm going to come here to just write the terms which is left. From the colors which is with the dark, I should say yellow, the terms which is left is going to be 3x squared times h plus 3x h squared plus h3 to the power 3. And I also see that I have 1 minus h there, divided by what? Divided by h. Oh, sorry, guys. Here it has to be, look at this one. I multiplied minus 3 to x plus h. I wrote here minus 3 minus h. It has to be minus 3h. You see that? Did you see what did go wrong? When you have minus 3 here, you multiply that. I had to just put minus 3 there. H cubed Then I have to write here minus 3h, which is left from here, minus 3h from here. It's minus 3h there. Okay, now it's going to be what? I'm just going to continue writing it. I'm just going to factor h. From these terms, I'm going to factor h, and let's see what happens. If I factor h at the numerator, what's going to happen at the rest of the terms? You see that when you look at the previous term, each term has an h inside. Then it means that that's the right time to factor one of those h. If I factor h from the first term, what do I end up with? I'm left with the 3x squared. From the second term, when you factor h, you are left with 3x h. And from the third term, you are left with plus h squared, because one of them is standing outside of the door, and you are left with what? You are left with minus 3, which is going to be here. Also, I know that still I have h. Okay, what is going to happen right now? I can see that I can simplify further because I see that at the denominator, I can see that at downstairs, denominator, and upstairs, there are two similar terms which has been factored. Then it means that I can just neglect them. I can just remove them, cancel them out. If I do that, what I'm going to have? I'm going to have 3x squared plus 3x h plus h squared. That's the thing which is left, minus 3. It seems that I have no choice except the fact that I have to go to the next page. Then where did I end up with on the previous slide was this. Imagine that if I call that function f prime of the x, what do I get? I got 3x squared plus 3xh plus h to the power 2 minus 3. Correct, guys? Any questions so far? Everything is fine?
Yes, sir.
Awesome. And now look at this one, guys. I said that on the previous slide that we always look at this, that h always has to go close to 0. Still, I have the same thing. I know that I have to push h goes to 0. I know that the h is not going to be equal to 0. There is a big difference of h equal to 0 and h gets close to 0. There's a huge difference. But for our case, we can always close our eyes and neglect that fact. At this stage, we say that we can assume that as long as h is gonna be very small, like the example which I had for you yesterday, if you make a comparisons between $1 million and 1 penny, you can get rid of the penny and say it's almost 0 for me. And because h is going to be very small, you can assume that it's going to be almost close to 0. Then as a result, if h is going to get close to 0, it means that the term that you have here, 3xh, it means that it becomes like that it becomes 3 times x times 0, which is going to vanish, huh? And also the same thing for h squared. It means that 0 to the power 2 becomes 0. Then if we assume these kind of characteristics of when h gets close to 0, Then I'm left only with 3x squared minus 3, which I had from there. Correct, guys? Did you understand the trick which I had here? That what does it mean when h goes to 0?
Yeah.
You can always approximate it. You say that, okay, h is going to get close to 0, but let's approximate it to be exact 0. That's what we did. But at the bottom of our heart, we know that h is not 0. We approximate it to the 0. And that's why you multiply 0 to 3x, and also h is going to be 0. And that's essentially, that's the equation that we love. Why? Because if I find the roots of these ones, because if I can show that, I can find some points like x naught, that f prime of the x naught is going to be 0, I can conclude that x naught, the roots of this equation, is essentially the crazy point or the critical point. And always remember, what is f prime? My f prime is this equation. F prime is this thing which we did together. F of x plus h minus f of x divided by h. When h goes to 0, it defines your f prime. You can call it anything. You can even call that you can call f prime of the x. You call it anything. You call that f apple of the x. For example, I mean, I mean that you do not have any restriction to what to find the functions which you have. Okay. Now, then as a result, the thing which I do, I come here to find the roots of this equation. I say that what happens if my f prime of the x equals to 0, then very easily you see that in that case 3x squared minus 3 should equal to 0. Then in order to solve this equation, how to solve this equation, it seems maybe initially a little bit intimidating, but look how easy is that. The first thing which I'm going to do, I'm just going to take 3 to the other side. Becomes what? Becomes 3x squared equals to 3. The next step which I'm going to do is divide both sides by 3, which then I've got left with x squared equals to plus 1. So far, so good, everyone?
Yeah.
Does anybody have any problems of how to solve this equation?
No.
Everyone is fine? Okay. Now, then as a result, the question is that, what is going to be the value of the x? Anybody knows what is the value of the x?
1 or negative 1.
That's so true. We get the value of the x plus or minus 1. Then I have, let's say, xc equals to plus 1, or I have x prime of c equals to minus 1. You see that if you put minus 1, square it, you get plus 1. If you get plus 1, square it, you get plus 1. That's a very interesting equation. That sometimes when I was at your age, I used to always make a mistake to find the second root, which is going to be x equal to minus 1. It took for me a couple of years to understand that when I have a function like x squared equals to 1, I should have 2 roots, plus and minus 1. Okay, now we got to, any questions, guys, so far?
No.
Everyone is doing fine?
Yeah, it's okay.
Great. Now, we find the critical points. Then, contrary to what we have seen yesterday, that when we have the quadratic functions, that we have only one critical point, and that one acts as a vertex line for quadratic function. Right now here with the cubic function, we see that we can have also uh, two critical points for a cubic function. Okay, now what's the point right now? Sometimes the purpose that we have to find these critical points or crazy points is that we need them for some optimization purpose to see which point is gonna be plus, which point is gonna be minus. Before I continue, yesterday in order to show the maximum or minimum, I'm just gonna review something which I did yesterday with you before I continue with the new lessons that we have for today. It's not part of this exercise that I'm doing for you. It's just a kind of a reminder of what happened yesterday. Yesterday, the method that we developed, it wasn't like that. We said that if I have a quadratic function, this quadratic function has a crazy point or a critical point. I call that here xc, and this one is going to be what? F of xc. We saw yesterday the general equation for this kind of quadratic function can be something like that. F of x becomes a x squared plus bx plus c. We talked about that yesterday. We said that yesterday if a, which is, we call that a leading coefficient of this quadratic function, if a is a positive number, then the function opens up. Then you see that the critical point that you get, it acts as the lower level of your graph, which we call that a minimum point. Then x of critical points is essentially x of mine. We had also the opposite one. We said that yesterday. If we have, for example, now this plot, and we show the plot like that, we saw yesterday that also in this case, they have a crazy point or they have a critical point, which we call that f of xc. You saw yesterday that for this graph also, for these plots, when you look at the general formats of the equation, that f of x is ax squared plus bx plus c, when we talk that the leading coefficients, that if leading coefficient is negative, the plot is opening downwards. In that case, we saw that yesterday, we can call this point as a maximum point because you see that you are at the top of a hill and xc is actually x of the max. These rules that we covered yesterday, they are just very specific for the quadratic functions. Then for the higher level polynomials, then we cannot use and apply them. They are not, you cannot use them. And now the thing that we just want to do right now, for these points, xc plus 1 and xc minus 1, we have two critical points. We cannot use that method. Now, then as a result, we're going to talk about a new method that we want to apply. Okay. Now, in order to move on and continue with this, I'm just going to introduce you with kind of an interesting technique. Look at this one. For this technique, I need a chart. And for my chart, I'm just going to show these two lines as the points for my critical line And also, I'm just going to put a different line which excludes my analysis. I'm going to assume the line which I have drawn here, the top line, is going to represent my x-axis. It's going to represent my x-axis. These two lines which I have here, they are going to represent my critical points. The first critical point which I have is going to be +1. The other one is -1. Remember, look at the priority of the numbers which I have decided, because as long as this direction is a positive direction along the x, then -x should stand behind the +x. And over here, I'm just going to write, I should say, the f prime of the x which I have drawn. F prime of the x is 3x squared minus 3. I'm going to write 3x squared minus 3. That's going to be the result which I got previously. Okay. And now, okay, what's going to happen? Look, and now here, please focus. How am I going to fill out this chart? Because the way that you're going to learn it now, you can use it for advanced function 12. You can use it for the calculus and vectors. And if you want to get an advanced placements in calculus, also you're going to use this method. And try to learn it as much as you can then. Then look at this. At these 2 points, which is x equal to -1 and x equal to +1, what is the value of this f prime of the x? It becomes 0, huh? Because these 2 points are the 0 points, are the roots of this function. Then as a result, these values produce 0. These are the zeros on these vertical axis. Okay, and now, guys, and now we have to fill out the chart, these 3 cells in the middle of my graph. But I have to fill out with the sign of the value of my f prime of the x. How to do that? I'm just going to start from here. Look at this. I'm just going to start. You have the choice where to start. I normally start from the middle one. I say, look at that. Between x -1 and x +1, there are infinite numbers, correct? I'm going to pick the one which is easy for me to find the value of f prime of the x. If I take x equal to 0, x equal to 0 is in between. That's right. I pick randomly x equal to 0 and put it in my f prime of the x. Then f prime of the x equal to 0 becomes what? Becomes -3, because you have 3 times 0 becomes 0. Then you multiply that by, then you minus it by 3, it's -3. This is a negative number, correct? -3 is a negative number. Then I can say that for any numbers, I have infinite numbers between -1 and +1. I selected randomly one number, 0, between these 2 numbers, and it becomes a negative number. Then I can say that for any other numbers between these 2 points, I'm just going to get a negative sign of my f prime of the x. Now, I'm just going to go back to the side, to the right side. You can go to the other one. It depends on you. I'm just going to go between +1, that it goes to all the way to +infinity. You can start on this x-axis from, let's say, from +1, go to 2,500,000, something like that. But the point is that we pick up a number which it makes the computation very easy. I'm going to pick up a number, for example, 2, x equal to 2. X equal to 2 is a good candidate because it is still in this domain from +1 to all the big numbers along the x, and it's easy to find a value of f prime of the x. F prime of x equal to 2 equals to what? Equals to 3 times 2 to the power 2 minus 3 equals to what? Equals to 12 minus 3, which is 9. This is what? This is a positive number, correct? Then as a result, I say that, okay, any numbers at the range of +1 goes all the way to the infinity. If I put that inside the f prime of the x, which I have there, it's going to give me a positive number. You see, you start by randomly selecting one number, and the sign of the f prime of the x with that number, it decides for the whole range of those numbers. Now, I'm going to go, this cell is left blank. I'm just going to come here to just fill out that part. I'm just going to also, because it goes all the way to the minus x or minus infinity, all the smallest numbers, I'm going to randomly select a number which stands between -1 and any smaller number. I'm going to do that again. I'm going to go ahead with the x equals to -2 because it's going to be very easy. At first, x minus 2 is smaller than x minus 1. It means that this is in this range. And also, computation is very easy to work with it. Then f prime of x equal to -2 equals to what? Equals to 3 minus 2 to the power 2 minus 3 equals to 3 times 4 minus 3 equals, again, +9. You see that? Which is still, again, a positive number. Then I come here and say, okay, at the range of x minus 1 to minus infinity, the value of f prime of the x, it's going to give me a positive number because a randomly selected number in that range gave me a positive number of f prime of the x. And also at these 2 points also, -1 and +1, which they are my critical points, I know that it has to give me a 0 number because these points are the 0 points of this function. Guys, any questions so far?
No.
Look at this. And now I'm going to go to fill out the third column. The first column on the top, it was the x range. The second one, it's filled with the signage. And the third one is going to fill with, let's say, a cartoon. What do I mean? Look at that. We have a positive, I should say. We have a positive sign here. It means that with the positive, we are happy. We have a negative thing there. It means that when everything is negative, we don't like it. We are crying. And again, the things are positive. Again, we are happy. Okay. And now, the thing which we want to do is this. We just start to walk. From here to check the faces. And at each point of the critical axis, we decide if we have a maximum or minimum. Look at that. When you walk from the left, when you walk from the minus infinity on the x-axis, you just go to the plus infinity to the x-axis, you see that still you are happy. From being happy, it means that you are growing. Or you can slightly show this like that. When you are happy, it means that you are growing. Everything is going up, you are happy. Suddenly you reach to a point, which is critical point, then you become sad, crying, which is essentially the same interpretation that you suddenly fall. That's why I showed that flash is moving down. You are happy, you are growing, now suddenly things changes, and you become weep, crying, and you jump, you fall. The same thing is still happening there. Again, you keep walking, you are crying, you walk, you get to a point which is x plus 1, still you are crying. You get to a point, suddenly you smile because you are growing again. And now look at this one. What these things means. Look at this case, at this scenario here. When you were laughing, you were crying, then you just started to weep and you are going down. What this top reminds you of? Of a maximum point, huh? Look at this top. If I connect these two flashes together, you see that? You see this point here on the top? It reminds you of the maximum point. You're at the very up. Now you just start to cry, you cry to reach to a point. Then suddenly you start to grow and you smile. This point reminds you of what? It reminds you of the minimum point. Correct? Any questions, guys?
No.
Everyone is doing fine?
Yes.
Awesome. And now look at this one. And now at this stage, we discovered that when we had two critical points, one of them at x equal to minus 1 should be our maximum point in the graph, and the other critical point, which is plus 1, should act as a minimum point on our plot. It's going to be the lowest point in our graph, and this one is going to be the highest point in our graph. Does it make sense, everyone?
Yeah.
Yes? And now, any questions?
No questions.
I hope anytime you feel that you need to see what kind of story did I follow to say that why this is going to be the maximum, why this is going to be the minimum, always look at the story which I told you. You can have a functions with 5, 10, or 9 critical points, and that's the strategy to find which of your critical points is going to be maximum, which of your critical point is going to be the minimum one. You see that how the signage changes at the boundaries. These boundaries that the sign changes, it acts either as a maximum or as a minimum. You can have another third critical points, you do the same strategy. Now, based on our prediction, x equal to minus 1 acts as the minimum number, then x equal as plus 1, x equals to minus 1 is a maximum number, and x equals to plus 1 is going to be a minimum number. Okay, and now I'm just going to stop the share and go to the Desmos to plot the function to see that if they have been correct or not. Okay, now let me share the screen on the Desmos. Okay. Everyone has the shared view of the Desmos from my desktop?
Yes, we can use
Okay,
Desmos.
fantastic. What was the function? I forgot it myself. Oh, okay. The functions which we had was this: f of x equals to x to the power 3 minus 3 times x plus 1. It was our function which we just ran to find the critical points. Okay. Look at this function. I have two critical points. The critical points should act as a local maxima or local minimum of the plot. Look at this one. These points, which I'm just going to find the coordinates of them, is the ones which we find. The critical points which we understood from our method, it was one of them, it was -1, which you see it here. The other critical point, it was +1. And it's very easy to find the y value. You simply plug 1 into this equation, becomes 1 minus 3 plus 1, becomes -1. And you want to find the value of the functions for -1, plug -1 there, you get it to be 3. It's very easy to find the corresponding value along the y-axis for these critical points. Extremely easy. But look at these ones. These critical points that we found, analytically, it's correct. And at the same time, look at this one. -1, it's the highest level at the critical point of the function. And the +1 is the minimum one. It's at the bottom of our function. Then it means that the thing that we derived before we just come to the Desmos, when we worked on that analytically, was correct. And we were able to predict the behavior of the functions as the local minima and the local maxima without even plotting it, without even seeing what's going to happen. It's as if you're going to say what's going to happen tomorrow from right now. You're predicting, you're foreseeing what's going to happen. And that's essentially what we did. Guys, any questions?
No.
Everyone is doing fine?
Yeah.
Okay. But before we just finish and we just go for our break, I'm just going to remind you of something. If you have noticed, I keep emphasizing to say we are working with the local minima or we are working with the local maxima. Why do I say a local minima? For example, look at this plot. I say local minima and the local maxima because we look at them as a local in contrast with the word which is global. When we say the local, it means that something happens at the very close neighborhood and we cannot see what happens. Let's say, for example, imagine that right now you are in Toronto, you can see which, for example, which building in your neighborhood is the tallest one, correct? If you watch outside from the window of your house, you can see in your neighborhood which building in the neighborhood is the tallest, or which building in your neighborhood that you can see is the smallest, correct? But you cannot see which building, let's say, in Vancouver or in New York in the United States is the tallest one. Can you see that? Of course, no, you cannot see that. Then the knowledge that you have in order to see which building is the tallest one or the lowest one in your neighborhood, it's restricted by the things that you see. And that's why we say that the tallest building and the lowest buildings that you see in your neighborhood, they are going to act as the local tall building or the small building. They are local. This is in your neighborhood. That's what we call them, the local buildings. But globally, it means all over the world. Of course, New York may have the tallest buildings that you cannot find it. You couldn't see that from where you live. Then that's why, for example, the Empire State Building, for example, in New York becomes the global tallest building in the world. And that is essential like the things that we have in our plots and in our functions. These two plots in our plot that we have for the critical points -1 and +1, they are going to be the local maximum and local minimum, essentially as similar as what we have when we say that, for example, one building is locally tallest one building is locally smallest, but we may have highest points in our plot that we cannot see them. For example, if I minimize the plot, you see that you can see the plot is going all the way up there from the right at the first quadrant, or the plot is going all the way down there at the third quadrant, but we cannot see them, where they show up, the maximum or the minimum. You see that? I can even minimize it and it becomes crazy. It becomes like the New York with your neighborhood in Toronto. That's why we say these 2 points, they act as local minima or local maxima. Okay, the lesson for right now is done. Any questions, guys?
No.
Everyone is doing fine?
Yeah.
Okay. How about Allison, Bo, and Yuchen?
Yes, teacher.
You're doing fine,
It's
Allison?
okay.
Okay. How about
Yeah,
Yuchen?
it's okay.
Sorry, Allison, you're fine?
Yes, teacher, it's okay.
Fantastic, fantastic. How about Bo and Yuchen?
Yeah, I'm good, sir. Thanks.
Fantastic. Yuchen, how about you? Yuchen? Okay, maybe he just went for the break much earlier than what we are going to do right now. Okay, the time is 11, I should say, to 20. Today we get, I should say, 15 minutes break, I think should be fine then. Guys, please come back by 1:25, okay?
Okay.
Come back by 1:25. We just continue from there then. Enjoy your break, and don't forget to watch outside to see which building is local maximum. Okay, see you by 1:25.
See you, sir.
See you later. A kind of shortcut. This is a scientific way to do that, but I'm just going to give that to you right now because it's going to be very relevant to the quadratic functions and all sorts of polynomials. And you can just take a note of it, and specifically you will see how these things make sense, and you can prove it when you just go to the calculus class and advanced placements calculus class in just a couple of years. But now I'm just going to give you a very easy descriptions. Then we finish the session today. Then you can just continue working on the materials on your own then. Okay, we say that if I have a polynomials like this, how much time do I have? It's okay, we have 15 minutes. It's going to be an easy way to just find this rate of changes. You do not need to just do lots of calculations and cancellations. We said that if f of x is going to be, let's say, a, for example, 3x cubed plus a 2x to the power 2 plus a 1x to the power 1 plus a naught. We say that in order to, it's a kind of a shortcut. We do not prove it because it's going to be beyond the scope, but we just start by the, I should say, the cubic functions. The functions which you have learned, I should say, in the functions 11, that's the quadratic functions. We say that this is going to be the, for example, the functions that you have, it's a cubic functions. And also we say that A3, A2, and A1 and A naught here, they are the coefficients of these cubic functions of a single variable functions, which the variable is going to be the x. And we say that in our case, that all of the coefficients A3, A2, A1, and A naught, all of them are real numbers. I'm going to say that, okay, in order to find, imagine, for example, for this one, to find the critical points, you saw that you have to come here, for example, we call that f prime of the x, which it was this function. We said that it's going to be this function. We said that we just find the f of x plus h minus f of x divided by the h, and at the end we said that we push h goes to 0. That's what we had done so far with the quadratic and with the cubic function. Now, I'm just going to show you something that you can solve these problems based on advanced math, but in more efficient way. What do? We say that, okay, you're going to see the proof in just a couple of years, but we are going to do this one. We say that f prime, if I have a function, that function is going to be, call it a x to the power n. N can be anything. When you want to find, I should say, let's say, when you want to find the critical points, and when you're looking to find the f prime of the x, if you say that my f of x is going to be this, I got a better idea, sorry. We say this one here. We saw that for the f prime of the x, we had to just deal with the monster. Sometimes I call this expression a monster. Something that we have, it's very unpleasant. So much to deal with, especially with the cubic functions when you have, for example, the other exponents. For example, when you have x to the power 3, you have x to the power 2, and also x to the power 1. You see that it becomes very nasty when you just want to deal with this monster. But there is another method, which I'm going to show that to you. I call this method a lifesaver. And we say that the f prime of the x, it's going to be as easy as that. I say that it becomes 3 times the initial coefficients which I had, plus 3 minus 1, plus 2, the initial coefficients you had, x to the power 2 minus 1, plus a1. And that's gonna be the functions that you can just solve it in order to find, I should say, the critical points value. I'm just gonna simplify that a little. We have 3 times our initial coefficients, x to the power of 2, plus 2 times a2 times x, which is going to be the power 1, 2 minus 1 becomes 1, plus a1. Okay? And now I'm just going to give you an example like that. I'm just going to come here and I say let's find an example. You can expand this method even to a polynomials of degree 10, which we do not go that direction. I'm just going to give you this one that sometimes it helps you to correct your work. If in the questions in the exam, I ask you to just find the critical points or the local minima and the local maxima of the quadratic functions or the cubic functions, and you are messing around with this monster formula, you can find this method to see that if you have done it correctly. Imagine that I have f of x. It's going to be, let's say, 4 times x to the power, let's say, 3 plus 10 x to the power 2 plus, let's say, 5x minus 7. Okay, this is going to be our example, which I designed it here to find the f prime of the x. We see that the f prime of the x, we just follow this lead which we have. We say that we take these coefficients. Look at this. I take these coefficients, drop it here next to the 4, and multiply it to the 4, which it means that I have 4 times 3 in x, which the power of the x now becomes 1 reduced to plus. I have the same thing. I have the exponents 2. I take 2, drop it next to the 10. It becomes 10 multiplied to 2 times x to the power what? I reduce the power by 1. You see, I have reduced the power always by 1. 3 minus 1, 2 minus 1. It becomes 2 minus 1 becomes 1. And eventually the last term, for the a1, I write it plus 5. That's essentially the same thing, because if you imagine that the power is going to be 1, you drop the power 1 in front of the 5, which is 5 times 1, then you are left with the x, which the power is 1. You say that 1 minus 1 becomes 0 then. Then x to the power 0, you know it becomes 1. Then essentially at the end, what is going to be our f prime of the x? It becomes 12 times x squared plus 20 times x plus 5. You see, I didn't, and that's the final answer. I can come here at the later stage, find the roots of this function to find a critical value and decide which of them is local minimum, which of the other one is the local maximum. Okay, then as a result, the thing that we do here, essentially we are done. This one was a shortcut method that you can do. And any questions, guys? There is no need that you master this method. It's a shortcut, the easy method that you can always double check your work with. Did you understand it?
Yes, and where did the -7 go?
Sorry, what? What, Tom?
The original equation there is -7, but the last equation there isn't -7.
Oh, that's the property of that. The constant coefficient, look at that. Go back to the main equation. Look at the a0 there. It's a constant coefficient. That's right. When I find, I should say, look, compare this to this method we have here, the a0 is gone. The constant coefficient is gone. It's killed. You do not write it. And the same thing here. Look at that. The 7 here is a constant coefficient. It's going to be removed when you write f prime of the x. You do not have to write it.
Okay.
Yeah. This is a kind of a shortcut. This is, you prove these methods when you just go to advanced placement calculus and vectors class. But at this stage, I represented that to you as a method, as a shortcut method that you can compare your end result with. For example, we have almost 5 minutes. Let me go back to the previous slides that we had today. You see the beauty of this method. Look at this one, guys. The functions which we started with today, do you remember before we just go to the break? I just gave you a function, which this function was a cubical function, because we had, let's say, we had a power 3 in our function. Remember, it was the functions that we started to work with. Look at this. We had to take all these calculations, simplifications, to get to a point that f prime of the x was how much? 3x squared minus 3. You see that? Now, we had to take all these steps to get here. I'm going to come here at the next page here. I'm going to show you that with this method, how can easily we can find these ones. in the 4 minutes that which is left from the class. We said that f of x, it's going to be x to the power 3 minus 3x plus 1. And I just want to find, I should say, the f prime of the x in order to find the critical value of my function. In order to do that, I'm just going to follow the same trick which I learned. I see the power of x cubed. I'm going to roll it comes in front of it and to be multiplied that to the power 1. It means what's going to happen? It means that then it becomes 3. It falls to the previous coefficients, which is 1, multiplied to the x. However, I know here that I have to subtract the power with 1. Then initial 3 becomes 3 minus 3. 1 becomes 2. Correct? For the next one, look at that. The power of this equation is 1. I'm going to take 1, slide it in front of the original coefficient, which it means that it becomes minus 3 times the power, which is 1. And I'm going to get x. But however, x, the power is 1. I know that for this one, I have to subtract this one with 1, which it means that the power becomes what? The power becomes 1 minus 1 becomes 0. And also, the coefficients which is left here without any variable is going to be turned to plus 0. It's going to be 0. Let's simplify that. Let's see what do we get. Then we get f prime of the x equals to 3 times 1 becomes 3, becomes 3x to the power 2, minus 3 times 1 becomes minus 3, x to the power what? 0. What is that? X to the power 0. Anything with power 0, it takes you to the 1. Then it means that it becomes 3 times 1 becomes the 3 itself. And look what we have done. And please compare this 3x squared minus 3 with the previous slides that we took all these nasty steps to get there. And you have 3x squared minus 3. You see that? This is a kind of, I should say, a kind of a shortcut. You do not have to learn it. In case you can just learn it at the end of your calculations that it becomes nasty. For example, you have taken all these steps with bigger questions. Imagine we had x cubed plus 2x squared, then you had more terms in between. Then it becomes confusing. You can follow this method, but at the end, you can use this method, this shortcut, to find the answers of your question then, to see that if you have done correctly or not. Any questions, guys? You do not need to learn it. I just said that in case if you want to learn it. Any questions?
No.
Okay, now let's do, I'm just gonna go back to stop the share. Before we leave, I need only 3 seconds to ask you the question, guys. Please, guys, for the homework, please go back to, I should say, page number 153. And for page number 153, please, the thing that you do, you use the methods that we learned today in order to solve questions number 4 and question number 5. And please send it to me on Schoology then. Then the homework for tonight is question number 4 and question number 5, page number 153 of the textbook. Okay. Then if you have no questions, guys, I think that's going to be a right time, as this is now sharp 2 p.m. to finish the class. And if you have any questions, send me a text on Schoology or email me. I answer you back then. Okay. Guys, if you have no questions, we finished the day today, and I wish you a very nice day then.
Okay.
Have a nice day, guys.
You too. Thanks, sir.
No problem. Thanks, everyone. Have a nice day. Bye, Time. Bye, Allison. Bye, Bo. Bye, Yuchin.
Bye.
Bye, Allison. Take care.
Take care.